Welcome again to the NPTEL course on storage systems. So, let me first summarize what we have done so far in the previous 15 classes. I first introduced what storage systems typically deal with, and then we started looking slightly into some more detail. In the beginning, I looked at the device level, for example, the disk, what kind of scheduling is useful at that level, without thinking about what goes on up there, just purely from at the lowest level. Then, since most of the systems have multiple components and they have a protocol by which they talk to each other, we had to look at the protocol level. And the types of protocols that we looked at was SCSI and iSCSI. The SCSI one typically at the electrical level, iSCSI at the network level or internet level. But this was using the block level protocols. Then we moved down and we looked at the file level, NFS level. And we noticed that NFS had some problems with consistency. Okay, that's the first time we noticed some consistent problem, because we are now coming closer to the application level understandings. When we are here at this level, we had no idea about what application was doing. As we come up, we start thinking about application a bit. So, that's the reason again the difference between block and file also is somewhat connected with application level understanding. Block level is strictly an internal affair of the file system or any other storage system that is below the let's say application/file level. Okay. Whereas NFS already there is some kind of application understanding. Okay. We expect files to have certain information in a particular way, the way I put it in. So, we start thinking about semantics at this point seriously. And as we go up, we are building larger scale systems, they're distributed. NFS also is distributed, but it is a slightly more simpler model. It is basically a server client model. When I'm talking about distributed system, we're talking about not necessarily only as a server and a client. We can talk about multiple systems working together to do something. Okay, that's what I'm calling distributed system. Okay. And here we have to face important issues that NFS started facing, the NFS, of issues of consistency. Again, NFS, because of its weaker model of consistency, it went through some iterations. Widely used one, then became NFS 3 and NFS 4. So, there are two issues that systems at this level try to handle. One is at the level of consistency issues, it could be issues and ordering issues. All three things are somehow have to be handled. Okay. We are going to take into account failure systematically later, but we already had to start thinking about it. That's why in our commit and consent protocols, we talked about failures. And then once we have a distributed system, we have to communicate. That's why ordering is important. There are multiple tests ordering at the network level or at even at the application level, system level. There are understanding things should be ordered. We looked at this also. Okay. So we have looked at some of this, but there are quite a few more things to look at. So I'll briefly mention what other things we have to also have to look at. And in passing also I'll mention other things we touched upon in the previous 15 classes. For example, we looked at briefly at storage characteristics. For example, why we can only choose 2 out of 3 here, caching, naming versus storage, difference between metadata and data. There are some recursion issues, whether we value metadata or data, how do we handle those things. This we just briefly touched upon, we didn't really talk about it, which we'll talk about in archival storage. Okay. So, as part of what we discussed so far, we also touched upon some of these issues, except this one in any. Okay. So, what we need to look at also later are issues like scalability, and so far with respect to scalability, we looked at some of these issues. For example, difference between networked and distributed storage. Network storage, a prime example is NFS. And distributed storage is something which is not used, but you can see, for example, GFS2 is an example of which Red Hat provides, that is an example of distributed storage, or a clustered file systems, which many companies provide, like for example clustered VXFS, that's kind of a distribution, because they try to give you POSIX kind of storage, POSIX kind of model. Again, as part of all we discussed, we also looked at notions of consistency as understood by file system database. I've not really talked about volume consistency, we'll talk about it later. We also touched upon issues regarding transactions, ACID versus non-ACID kind of models. Again, with respect to commit protocols, we looked at 2-phase commit, 3-phase commit back source, and we also touched upon the CAP theorem, and because of this we had to think about slightly relaxed models of consistency, eventual consistency. So far this is what we have done so far. Let's see what else we have to look at. Okay, there is a lot more things to come on the scene. First of all, we not really touched upon distributed locking in the presence of failures, which is an important issue. Okay, when I'm building a distributed storage, I have to handle this part, and this contains everything in one place. Issues regarding ordering, in terms of applications understandings, in terms of interactions with file systems, applications, all those things, failures, all these things keep coming here. Okay. Again, we touched upon a bit on scalability, but there are newer notions of scalability which we also have to handle. For example, if you are going to scale to web scale systems, we need to have even more different models of scalability that we are going to start thinking about soon. Okay. Again, when you build systems of, again, the web scale, reliability becomes very important, and that we have to look at. Again, a good example of something which handles both these things, for example, we discussed again in the very beginning, a Google file system does both of this, but it is for a specific application for search only. It's not for other applications. For example, it is good for read heavy workloads, but not so much for if workloads which involve a lot of writes also, or if they have small writes. This is usually good only for big objects, okay, the Google file system. So we have to look at this also. There is also an issue of security, which are not really touched upon at all. It's a big issue, because finally data has to be secure. Okay. Without this, the whole thing falls apart. And so operating systems give you some notion of security. You may need to make it slightly stronger. Okay, that also is there. Also, quality of service, we briefly touched upon it with respect to disk scheduling, but we're not really seriously looking into it. This is a very big issue, which also has to be looked into. There are also issues concerning cross-layer optimizations. How do we ensure that, is it possible that if I know the device characteristics, I do my file system in a different way? Okay. So can I optimize across layers? What do I do about those things? That also is a big issue. And one very big issue is archival storage, which is about how do I make sure that if I write something now, somebody can read it 15 years from now. Now, this has to be resilient with respect to device changes, file system changes, operating system changes, language changes, okay, and various other kinds of things, okay, which is non-trivial. Okay. It's a very, very difficult issue. So actually, there are no serious answers so far. Okay. And in connection with that, we also need to look at other storage designs, okay, with respect to newer devices. Okay. This also we not looked at. So it's quite a bit of stuff to go through. So far we have covered a part of it. So today I would like to look at distributed locking in the presence of failures. Then we look at some of these issues, each of this in some detail. Okay. I'm going to present one simple lock protocol. Again, the real distributed lock managers are very complicated. And if you look at Netware or Sequent, some of the companies, they made their name only because they had a good distributed lock manager. Okay. And this particular lock protocol is not going to be as complex as those ones. Actually, it was designed by one of my students. So it is a good, simple, reasonable protocol, which may not take everything into account as industrial strength distributed lock managers can do. And so we are going to look at this briefly, so that to give an idea about what kind of issues that crop up. What are the requirements? There should be no single point of failure. Whatever happens, the lock state should not be lost. Because if the lock state is lost, then somebody can try to update something without realizing somebody already has got a lock. If you have a failure of a node, it should release locks held by it. Okay? Should minimize number of network hops, avoid as much possible. I think we saw some of it in the case of the Berkeley XFS, where they do forwarding of reads, right? And that's why we got a deadlock situation developing, right? Because of that, right? So it's an issue. And if you are trying to get, if somebody has got the lock state, then you might want to figure out, you may want to revoke it. The question is, do you wait for everybody, okay, till the response say I don't have the lock? Okay? So it's preferable that you have a system that is not waiting for the slowest party, okay. And the various types of ordering that we have decided, we looked at FIFO ordering, causal ordering, total ordering. I don't want total ordering. Total ordering is too painful, too slow for words. Okay. So I want something better, either it should be FIFO or causal. So I want my design should handle one of these things rather than the most restrictive form of ordering. Similar, this is similar to in the architecture area, you have various memory consistency models, and you will see that there are models like sequential consistency, then release consistency, etc. Right? Typically, the sequential consistency is the most restrictive form. If you, the easiest for the programmer to write applications in that particular model, but the most restrictive one. So people of most architectures don't provide it. Okay. Here also we don't want to have our lock protocol depend on total ordering messages. That means it can only depend either on, we will assume that we can write this protocol assuming only either causal ordering of messages or FIFO ordering of messages. That means we are already assuming there is some kind of GCS, group communication system, already present. Okay. And the lock state should not be in one single place, it should be distributed. Of course, if you take a SPOF into consideration, it cannot be everywhere. The actual protocols, actual details of the implementation are far more complex than what I am going to discuss. If you are curious, you can look up the thesis written by the student. His name is Gautam. Okay. Okay, let's look at the lock protocol. So what is the issue here? The various clients who are requesting locks, they are running on various nodes, and you will find that there are multiple threads in each node. Any thread can be accessing a particular lock. So there is a local agent at each node, and then if the thread makes a request and it's not available at the local node, the agent will actually make a request, basically does a single multicast for the lock and expects the lock. It wants to get it from somewhere. Now to take care of some bootstrapping situations, when locks are not owned at all, you have some kind of initial lock server. Okay. When nobody is there, nobody can respond, right? No, the lock is not taken, right? There is no one to saying that I have the lock. That's why I have a bootstrap situation to take care of. There's something called ILS, which is available, which can actually see that nobody has requested this lock and it can grant it. Okay. Of course, the minute you have something like initial lock server, you have to think about what happens if this fails. Okay. Does somebody keep waiting for saying that whether the lock is taken or not. Okay. So your group communication system should actually be able to notice any lock fail, any server failure, and be able to restart things or come up with a new group. Okay. That's something that has to be done. Okay. This initial lock server needs only to store lock IDs. You don't want to store the complete lock state. Okay. So I will not discuss this further. Okay. There is, it turns out this is enough for the time being. It's enough. Okay. Locks once granted are cached at the holder, that is the node, and corresponding data also cached and returned back. Okay. basically you need to have some notions of cache coherency. If locks are unused, they are sent back to ILS through another separate protocol called abricate protocol. I am not going to discuss some of these aspects that in detail. Okay. I want to only concentrate on those aspects which will tell us something about the kinds of issues we discussed about ordering. Okay. Because this distributed lock manager is important component in a distributed file system, and so I want to look at this, especially where writes and reads are, they're not skewed. It's not only reads and only writes. You both have mix of this thing. Therefore, there has to be some locking that has to go on. Okay. So now let's look at the kinds of things that can happen. Okay. Now let's say that A has the lock and B and C are both making a request. It turns out B's request comes to A first, and A sees this request and then grants it to B. C's request is also made, but let's say that the C's request happened this way. C's request come to B, and B scratches its head and says, I don't have a lock, so I just ignores it. Same thing with C, okay, this request to A. A also says, okay, I've already given it, I can't do anything with it, I'll just drop it. So what's happened to C's request? C's request is lost. Okay. Now you have to, it's a very simple case, trivial case, this has to be handled. How do you handle this? You somehow have to buffer the request, because the fact that C made a request, right, somehow has to be buffered by D also. Okay. So there has to be some queue of some kind. Okay. So lock holders queue lock requests if they have locally locked the lock. They have to queue the locks, queue the requests. So basically, even those guys, for example, B also has to queue the request. Otherwise, the C's request will be lost. Requests are granted in FIFO order to prevent starvation. Again, as I mentioned, this is one particular design. There are lots of possibilities here. Okay, I'm just showing you one example of what one of my students did as a solution to this particular problem. There could be better ways of doing it. Okay, but for us, the issue for us is when a node is in transit. What does a node in transit means? Basically, somebody has a lock and it has been given to somebody else. Okay, so I think it should be when a lock is in transit. I think it's a mistake. What happens? The lock could be unknown at the previous owner, the lock could be unknown at next owner, basically because the delays that are there can be so substantial that if you go to this guy already has relinquished it. It has been given to this guy, okay, that also has relinquished it. Okay. So the thing is that you cannot really depend on the fact that let's say the current owner or the next owner also will have it. It could be anywhere, we don't know. Okay. So that's something which has to be figured out. Okay. So as you mentioned before, one solution is if we can queue the requests even at sites like B, so that we know that C's request cannot be dropped. Okay. That's the reason why we do this. But this itself causes some additional problems. Okay. Basically, you can see what is happening is that the somewhat distributed state, it has to be properly taken care of, and the messages are coming in arbitrary order depending on the way things are getting delayed, etc. So that's where to have a clear, correct snapshot is non-trivial. So it turns out that some requests can be obsolete. Okay, you can look at the you can queue the requests, but some requests can be obsolete. Let's look at this one. See, for example, B requested it, A gave it to B, and then what happened was C requested it, and B in the beginning also had requested to C. If I queue all the requests, then when C gets it, that after B has got it, it will still have B's request still sitting here. Now you have to notice that also. Okay, it's a very obvious thing, but you have to handle it. Okay, because notice what has happened. The very beginning, B decided it wanted a lock, therefore it sent it to everybody. So C has queued it because for this particular reason, because I didn't want C's request to be there. That's why I did that. But what has happened is that once B has got it and gives it to C sometime later, an obsolete request of B is sitting out still here. That also has to be handled. I'm just giving you some of the kinds of things that really happen in a proper, if you're really looking for consistency in a LAN or a, let's say, distributed storage kind of system, these messages can get rewarded in arbitrary ways. And you have to be correct with respect to all these orderings. Okay. So we can see that one of the lock requests is obsolete. How do you know that a lock request is obsolete? You can see that I made a request here. This is, if I am using, there is some way of finding out that this B's request to C is obsolete because I already got a lock. Then I can drop this. Then when C gets a lock, it uses some technique by which it figures out that this request is obsolete because B also already granted a lock. Okay, if you are able to drop that one, then everything is fine. But this requires you to have a notion of distributed time across all these nodes. That's why we need a vector time clock. Again, we discussed it in the previous class. Right? We need a vector time clock model. Then I can figure out that this request, which is sitting here, is obsolete because B already had got the lock. Okay, it's done. Okay, and C, when it sees this particular request, and then when it gets the lock, if there is a way of timestamping that lock when it got here, it can see that it's obsolete and throw it out. Okay, that's something we have to do. Okay, so what we do is we flush obsolete requests by having a logical time on each node. Every request that is sent is stamped with the current time. Locks carry a timestamp also, which says when this lock was last held by a particular node. For example, when B got it, there will be a timestamp on it, and then you can see whether C can decide that B already has got a lock, so I can flush this obsolete request. Okay. So basically, the protocol, we increment the logical time on the node and stamp this on the lock each time we grant a lock. So we have to keep track of all these events. The timestamp on the request is less than the time on the clock, the request is obsolete. Okay. Lock requests greater than equal timestamp are valid. Okay. And initialization conditions also have to be taken care of. Okay. So this is one example. But it turns out that this is not enough. There is some more need for. So right now, so far we can do FIFO we said, but there is also reasons for doing causal message delivery. Okay. Now let's see what this causal message delivery is about. Again, we are assuming a certain type of message ordering that happens. So C makes a lock request and B also makes a lock request. But by sheer bad luck, C's request comes to B before B has made it, but C's request to A comes after A has granted it. Now again, what will happen? C's request to B doesn't have a lock at this point. Therefore, B will drop it. Let's say B drops it. Okay. Okay. Or suppose A drops it also because it doesn't have it. Then we have a problem also. Okay. Even if you use the previous solution, buffering doesn't work. Actually, what you have to notice is that C's request came before B's request, and therefore there is a need for a causal ordering. Okay. We discussed causal ordering, and that's what has to be employed here to take care of this particular situation where C's requests are essentially not being handled properly. Okay. You notice that if you don't use causal ordering, there is no, the FIFO ordering doesn't help us, because see, this C, right, is talking to these two guys and B is talking to these two guys, and there is no way to order them in a FIFO mode. There's no, they are incomparable. Okay. But from a causal point of view, it's possible. Okay. So this particular design takes into account that you can order messages either in the FIFO way or in the causal way. Okay. These are the only thing assumptions. We are not assuming any total ordering. Of course, to be completely sure that this particular protocol works, you need to formally model it and check everything. Okay. And this was not done, so there could be a bug in this protocol still. I don't guarantee it is a completely correct protocol. Okay. And there are other issues also which have not been taken into account, because it runs on real systems. There are issues like interrupts, system calls, etc. are there, and they also may actually, if you get an interrupt, it may not be delivered at the right time. It may be delivered only after the system call exits. So various reorderings are taking place at different levels in the system. So a real complete solution has to take into account all these things. In addition to, at this level, there are levels below where somebody else could also be doing reorderings. Okay. Unless you are clear about it, or unless you take some measures to make sure those kind of misorderings take place, you cannot really guarantee correctness of this. Okay. So that hopefully gives you some idea about why you need causal ordering. And so if you get causal ordering, you can very clearly see that C requested it before B, and therefore A can try to attempt to give it to C rather than B. Okay. So there are some things we can try, okay, if you have the causal ordering. Okay. So now if there is a failure, let us say of the ILS itself, okay, you have to rebuild the states, the union of states from all the nodes. Okay. So there are other things that you have to do. For example, you have to flush all the messages, which includes the log grants. Okay. So basic idea is that you want to get it to a clean state, and therefore what we are trying to do is that no lock request should be on the wire at that time. Okay. That's basic idea. Okay. You want to get it to a particular state where all, essentially the state is in a known simple state. Okay. Otherwise, you need to do something more complicated, what is called distributed consistent snapshot. Okay. Okay. So which makes it even more difficult to engineer. Okay. So now with respect to, you typically also need, in addition to this, something called reader writer locks. Now when you have multiple readers and multiple writers, you need to have some policies, and you can follow some of the kinds of policies that are used in regular mutual exclusion algorithms. Okay. Readers read, keep reading it till a writer comes in. Then what you can do next is, you can prevent any other readers from coming in. You give the access to the writer, drain out all the readers, then the writer gets it, then all the other readers who came in between, they will be queued, and then when the writer finishes, if there are no other writers, then the queued readers will come in. If there are other writers in between, then you have to again decide whether the queued readers or the next writer who has to get access to the thing. Those kind of things can all be written. Okay. That's not, those kind of issues are slightly easier to handle. The policy decisions can be handled. Okay. Now it also turns out that to perform some of the protocol activities, the primary reader also has to be electron among the readers, because somebody has to keep track of who are the readers, who are the writers vector, right? Because some distributed state has to be kept about how many readers are there, how many writers are there, etc. Okay. Again, this particular primary reader also can fail. Okay. You have to handle that part of it also. Okay. So there has to be some election that can happen multiple times. Okay. So once you have this a primary reader and ILS, probably they can watch for each other. There has to be some redundancy in some of these things. Okay. So again, as I mentioned, the code is substantially more complicated for this case. You need to handle multiple readers, waiting for readers to exit. Recovery is more complex. Via failure has to be detected by writers or by the ILS. Primary dies, all non-primaries have to perform duties of primary till ILS selected. So there is issues of this kind. Okay. So I hope I have given you some idea about some issues a distributed lock manager has handled. Okay. And this is just a simple design, and the idea here in this particular design was to use group communication systems primitives like causal ordering and FIFO orderings to the exclusion of total ordering mistakes. Okay. That was what this particular attempt was, and so the student was able to come up with a consistent working system. Okay. Not that it has been proved to be correct, but it works sufficiently that very large programs could be run on it. Okay. Now, so after this discussion about distributed lock manager, I would like to move on to a few other topics. I am not going to discuss distributed lock manager after this. Probably we may talk about at some point later possibly another lock manager. For example, Google's chubby lock manager, we probably want to look at it. We'll see. Okay, depending on the availability of time, we'll look into it. So now again, let's just do a bit of summarization of some of the things that we would like to look into and where we are. So let's just briefly look at the various types of distributed file systems that are available, and just take a look at some of those things. First of all, right now we will exclude network file systems, NFS, okay, because there the notion is strictly a client and server, multiple clients but a single server. What we are thinking about when we say clustered is that there are essentially, there is no such thing as a single server, there are multiple nodes which together behave like a single server. Okay. So you can have what is called a clustered file system, and you can either provide a POSIX semantics or a non-POSIX semantics. Now this issue of POSIX semantics and non-POSIX is a very delicate one. Various parties claim to have POSIX semantics, but turns out they, in some specific cases, they don't provide it. So it's very difficult to figure out who is really POSIX, who is not really POSIX. I have given my idea of what POSIX is, whatever I understand of POSIX, what they are doing, what they are doing. For example, LusterFS in the documentation say that they are POSIX, fully POSIX compliant, but from what I understand, there are certain issues they don't handle, which is really POSIX related. Okay. So we don't really know. Okay. It depends on the interpretation. Okay. But there are some clustered file systems which are definitely POSIX. For example, CVXFS, the clustered VXFS is a clustered POSIX. They also have to play around with POSIX a bit to get efficiency. And for example, one of the kinds of things they do is the following. In a regular file system, you have what is called, there are, anytime a file is accessed, you have what is called A time, C time and M times. A time is access time, C time is create time, and M is modify time. Okay. Now, if you are in a distributed system and if you are making accesses, read-only accesses, then every time you do access time, then if it is the case that everybody else in the node should know about the fact that you accessed it, it's extreme. Basically what it means is that I am the only party who is using it, and if there is somebody else who has got it cached but is not really using it, he also has to be informed that access time has changed. Okay. Now that is a bit too much, okay, because that basically means that all caching and everything is absolutely useless. I basically have to keep on synchronizing the metadata across the whole system for every access I do, every single access, because every time I access something, the access time will change, even only for read purposes. Now that is intolerable. So the semantics of access time update has been relaxed. So they say they are POSIX, but if you think about it carefully, even the clustered VXFS cannot be strictly 100% POSIX compliant. That's the reason why there is some dispute about how you classify things. I have just given you my idea what it is, but this, I think I'm pretty sure that GlusterFS, they will say that they are POSIX compliant. Okay. And GFS2, the Red Hat provides something called GFS2, which also claims to be POSIX compliant. There are other file systems which avoid certain cases which slow down the system. For example, there is a system called Ceph, which tries to reduce the time taken for lookups, and there they may not be POSIX compliant. For example, normally when you look up a name, the name has got multiple components, so you cannot do a single lookup. You have to do multiple iterations to get each of the subpath names, right? Each of them has to be passed independently, and finally you get the full path. If you want to do a one shot lookup, then it's not possible. Okay. And why is that an issue? Because it's possible that if you do in one shot, it doesn't have the same semantics if you were to do it with part by part, because it's possible that some other concurrent activity is happening, and therefore if you do it in one shot, the result will be one. If you do it part by part, it will be some other semantics is possible. So that's the reason why Ceph, I would call it non-POSIX. Okay. So the other kinds of file systems like parallel file systems. Okay. GPF is a well-known parallel file system from IBM. NFS V4 also has some notions of providing parallel access to files. Okay. And Lustre also provides certain notions. Okay. So basically the idea here is that you have a very large file, it is subdivided into small portions, and each node will actually work on that particular portion. So it's sort of implicit partitioning. Okay. You don't take any locks, etc. It is clear that when you distribute the file across these nodes, the application has figured out some non-interfering ways in which some things are, the file is chopped into pieces, not really chopped into pieces, it is accessed or updated in parallel through a implicit understanding at the file system level or the application level. That's what is going on here. If it is done through the application, of course, then the file system is not in the picture. If it is done at the file system level, then the application has to tell the file system that please, I want a particular view of this particular file that has to be in 10, let's say, parts, and I am going to assign various nodes to work on each of those 10 parts independently. Okay. So there are various systems of this kind have some notions of this kind. Again, there are other kinds of file systems as we discussed before, things like Google file system and Hadoop file systems. Okay. And as we go down this one, we come closer to these notions of key value stores, which are basically quite removed from POSIX. They don't have the same semantics. Again, we discussed in the very beginning in the first few classes something about key value stores briefly. We looked at some of their APIs, right? And we will study this in some detail. Okay, we will look at these areas a bit. Okay, you will find that there are other types of file systems which are not really touched upon, which are also important. For example, you can have a file system like the ZFS, originally from Sun, and they actually provide very interesting guarantees with respect to consistency of the file system and the ability to incorporate the device management as part of the file system itself. And so this is a fairly well thought out idea about integrating device management and file management, and it gives you reasonably good reliability guarantees. And so similar to ZFS, in Linux we have something called BTRFS. I forgot to include it here. There is something called BTRFS, which has got similar guarantees like ZFS does. Basically, these are designed taking into account reliability as an important aspect. So, one thing they try to do is, if you write something, you can either have what is called end-to-end arguments at the file system level or application level. If you are using ZFS or BTRFS, you are getting that end-to-end argument at the file system level. Of course, application also has to worry about that, because there could be some problem from the application to the file system. There could be some corruption of something is still possible. But if you do it at the file system level, already you are now guaranteeing that whatever happens, whether there could be some malfunctioning, host bus adapters or RAID devices or disk, whatever it is, you have some kind of checksum. And then when you read something, you check whether what you read has the same checksum as should be present. If it's not present, you can actually flag an error as quickly as possible. That's what ZFS does. That's what BTRFS does. Okay. So, this one ZFS basically currently is not a distributed file system as we have looked at this ones, but it is distributed in terms of devices. It can handle large number of devices. Okay. And so, it is distribution at the device level, not at the file system level. Okay. So, it doesn't have, it's not clustered as the way we are talking about clustering here. There are also other designs like log structured file systems, which are, I mentioned earlier that you can do some cross-layer optimizations. Log structured file system is an example of an attempt at cross-layer optimization, because you take into account the characteristic of a disk carefully. If you look at a disk, you will find that a disk is very good at giving you good bandwidth, but is poor at latency. So, if you are designing a system which has got reasonably good bandwidth, that read or write bandwidth, but is poor in terms of latency, then one of the design options is to make sure that you aggregate requests as much as possible, or you make sure that you do not have to do any seeks. Okay. You avoid seeks as much as possible. The log structured file system basically has an interesting design, which basically says that all my blocks etc. are essentially a log. Okay. In a normal file system, you will find that the blocks can be anywhere on the disk, and you will have to seek to a particular block to be able to read or write. So, latency is involved in it, because you have to seek to it. That seeking basically is a mechanical activity, and it takes about tens of milliseconds. Whereas in a log structured kind of file system, what you are planning to do is to ensure that seeks do not take place. So, the head does not move that much. Idea is to keep on writing without moving the head if possible. Okay. Only under recovery situations, that is wherever some error has taken place, unusual situation, at that time you go back and read. Okay. That means there you do seeks only on failure events, serious failure events. Okay. So, this is also another design option. Okay. So, various designs have been attempted with respect to distribution, with respect to device management, with respect to trying to do cross-layer optimization, etc. And there are quite a few more if you take into account things like security, quality of service, all kinds of things of that kind. Okay. So, we are not really gone into those things. So, what we would like to do is continue on what we discussed earlier, basically to try to see how, if you are trying to scale things up, right, what kind of options are possible. Okay. So, what we will now do is, instead of being let us say looking at POSIX as the model, we will decide POSIX is not that important. Okay. Let us say that. For scalability, I am willing to sacrifice POSIX compatibility. That means, these are specialized applications which do not require POSIX. Whoever is writing the application knows what they have in hand, that whatever system they are using does not guarantee POSIX kind of semantics. It is a special command semantics which you use. Okay. So, This is where you will find a lot of work happening now, and this also has been interesting because the issues with respect to whether for this large scale storage system whether we should use a file system or a database has also come into picture in a major way. That's why there is a slogan called no SQL, basically saying that, because this no SQL itself I think is a problematic name, but this basically is trying to say that the current relational database models cannot scale, okay, and the things that can really scale are slightly closer to the file system kind of models, okay. That's the reason why Google file system, the GFS does not really address POSIX, it's not really part of their design, okay. They have not gone for a database because the database will be not scalable, okay. And that's the reason, for example, if you look at the quote of one John Osterhout, he is a well-known operating system designer. He was also the author of this LFS, this particular log structure file system. He makes a claim like that he has not been able to find a single example where RDMMS has actually scaled, okay. They are good for consistency if it is critical information like monetary aspects have to be taken into account, but for the web scale applications where that is not the overriding concern, these RDMMS have not been able to scale at all, okay. Many companies which started with RDMMS have finally had to move away from it to a different model. I think if I remember right, Facebook started with a RDMMS, and then as they really became big, they had to essentially move their system away from this database model, okay. And if you look at it, Google file systems, there are something called column stores, which are a slightly different model compared to relational database models, because in relational databases you have the notion of rows. Here you basically keep information in terms of a column, and there are some positive things that come because of this instead of having a row orientation. Basically, the information that you keep in the row, for example, in a column, for example, is usually the same type of information, and therefore compression is better, etc. So when you are doing very large scale systems, this column stores have been also explored, okay. So basically this NoSQL kind of model basically says try to avoid the highly restrictive ACID model. It may be good for some critical applications, but it may not be applicable in many other situations. So the idea was to not go for ACID just like that, just carefully think about it. If you need to go for it, otherwise drop it, go for something else, it's more scalable. That's the reason why you will find that most of these big companies, they have not really gone for, they have certainly some small scale relational databases, but mostly they have gone for non-relational models for their storage needs. I think eBay is the only one I think here who is heavily invested still in relational model, because most of their thing is based on let us say auctioning kind of systems where a lot of monetary aspects are involved. I think these are one of the groups who are more heavily into relational databases. And the way they do scaling is by having per let us say what you might call product databases. For example, if there is an auto, they will have a database only for autos. If it is some electronic components like PCs, they will have only a complete database only with PCs. So they are distributed that way, okay. So again finally it turns out to be a single database, not a distributed database, because the real problem is that scalability is not there with respect to distribution, okay. So the other kinds of systems that people have come up with is for example, Google has come something called Bigtable, and it's a sparse distributed multi-dimensional sorted map, and we will look at some of these things later, okay, some details about this. Similarly, Facebook has come up with some model Cassandra, which has become an Apache project, okay. It's a distributed storage system based on the Bigtable model, and So we will also look at some of these issues. Okay. And Hadoop is similar to a Google file system, again open source kind of model. Okay. So what we will do is we will make our way through some of these systems of model. Okay. So let me just mention some aspects we can look into as part of scalability. Again, for most of these things we need to worry about how to guarantee three things, that is consistency and availability and tolerance to partitions. Okay. So I think we already mentioned it. First option is to say no ACID. Okay. Use a single version of database. Again, this has been followed by, as I mentioned, eBay. Okay. You scale across products, not you have each product has its own database and that is not distributed. Okay. Other thing to do is to have multiple databases and then you reconcile them somehow, manually reconcile them or use some semi-automated way by which if things go out of they become inconsistent, you do something about it to figure out how to make it consistent. Okay. The other thing is, if there are any partitioning that happens in the system, you defer the transactional commit until partitions are fixed and then the distributed transaction can run. That's one way to do it. But this is basically a availability sacrifice here. Okay. Or you can do eventual consistency model. Okay. Again, we discussed briefly this one. Okay. So eventually all copies of an object converge, which is probably weaker than what you might be happy, okay, in many situations, in some situations. But this is one that's available. Again, when you're designing big systems of that kind, you figure out where you can tolerate this and have it run that way. Where you cannot tolerate, you go for ACID. So, for example, Amazon will do most of the stuff using this model, but when it comes to billing and other kinds of stuff, they'll go using ACID model. Okay. Where finally the important aspects like money are being transacted, then you probably use ACID and use a regular relational database. So basically you have to figure out your application where some things are, what kind of consistency is appropriate, and then do something like that. You can also restrict the transactions, and this is what is called sharded MySQL. That is, sharded means you have break it into a few pieces, and shard is basically a piece. Okay, and then each piece is handled in one particular place. I think just like I mentioned about eBay. Okay, one node transactions, objects and transactions are on the same node. That is, you don't go across multiple nodes. So all these problems of cap, etc., are worked out. Okay. The other thing is one object transactions. Transaction can only read or write one object. Okay. This could be across multiple systems, but there is only one object transactions. That means that you are not concerned about the causal connections between multiple objects. Okay. You do it with respect to one object. Again, this is similar in computer architecture world. You will notice that there is some notions of memory consistency models. Okay. You have cache consistency models and memory consistency models. Cache consistency models take care of only things of a particular cache line, whereas memory consistency models talk about relationships between multiple cache lines. There is some causal connection. For example, if I do one thing followed by something else, I need to make sure that, just like what we discussed earlier, they might have to be made stable in a particular order. Similarly, in architecture also we have the same issues. Okay. And there are other issues which, for example, other kinds of models. I think I will not discuss this in detail right now. For example, Yahoo has got some other models. They work what they call timeline consistency. What they do is they keep various versions of a file, and your application can request a particular version. Okay. So there are ways to figure out which version, current version is there, and you can say that I cannot tolerate anything lower than a particular version. Okay. So, and they guarantee certain things about how, okay, these versions change. Okay. Well, copies may lag master record. Every copy goes through the same sequence of changes. Okay. So this kind of models are also possible. Okay. So this is, I'm not going to too much in detail, but basically there are other models also possible. Okay. So this is available in a system called Peanuts. Okay. Where this kind of models are available. Okay. Okay. I think in next class we will start looking at some issues regarding scalability, and we'll start thinking about looks like some systems like Hadoop file systems or Google file systems.